Hello guys, in today's video we're going to learn about Bellman-Ford algorithm for the single source shortest path problem. But before getting into the action, let's match our expectations. I'm studying this topic by myself and my videos depend on the wisdom of the crowd, a topic that really fascinates me. Therefore, if you find any mistake in what I say, please let me know in the comment section below. I promise to read all comments and re-upload if necessary. Also, please subscribe to my channel, I tend to upload many videos on this topic. The goal of the single source shortest path problem is to find the shortest path from a single vertex to the rest of the vertices. If the graph is unweighted, then the breadth first search algorithm can solve the problem efficiently. If the graph is weighted, however, we require a more sophisticated algorithm. Bellman-Ford algorithm designed on directed and weighted graphs. It doesn't work, however, if there is a negative circle in our graph, but it can detect such a circle. Let's jump right into it. Bellman-Ford algorithm for SSSP problem. Single source shortest path problem. This algorithm solves the single source shortest path problem for directed weighted graphs. It doesn't work, however, if there is a negative cycle in the graph. It does support negative edges, however. Here is an example of a graph containing a negative circle. This one. Now, as you can see, say we begin from this vertex and we are going clockwise, so minus 9 plus 8 leaves us with minus 1, and we are deducting minus 1 and got minus 2. Therefore, it is in our interest to make an infinity loop on this circle and never end the algorithm. The algorithm runs the iterations it must. Before it starts, it initializes an array with the names of the vertices and the weight of the shortest path to reach them. Except the path to the source vertex itself, which is 0, the cost to reach any other vertex is set to infinity at initialization. The algorithm starts from the source vertex, look at the edges from it, and update the distances to its neighbors. It then goes on all vertices which the distance to them is a finite number, and doing the same to their neighbors. Once the algorithm finished to review all vertices, it moves to the second iteration, repeating the process again all the way from the source vertex to the last vertex, in an attempt to find better path. The algorithm stops after an iteration in which no path updated. Let's see an example. So here is our directed and weighted graph, G equals VE. We want to find the shortest path from vertex S to the rest. We will set a table with the distances from S to the rest. Vertex S has two leaving edges, this one and this one, to vertex C and vertex D. We will update the distances to these vertices accordingly, since any finite number is smaller than infinity. And this is what we got. Alrighty. Vertex B, although it has two neighbors, but we cannot reach it just yet. We haven't found a path to it yet. Therefore, it is unreachable and we pass it on this iteration. Moving to vertex C, it has one neighbor, vertex D. The weight of that edge is minus 1. The cost to reach C is 3. Hence, the cost to reach from vertex S to vertex D via vertex C is 2. 2 is smaller than 7, so we update the path to the best one found. This one. Great. Vertex D has one neighbor, vertex B. So far we haven't found a path to it, to vertex B, and it was stayed at infinity. Now we can update it to the distance to D plus the cost of the edge from D to B. The weight of the edge is 4, so 4 plus 2 equals 6. We update the path. Great. We finished the first iteration. Resuming with the second iteration starts again from vertex S. So, vertex S has two neighbors, C and D. but the path to them is longer or equals to what we had already found, so no update here. See, the path to vertex C is 3, unchanged, and the path to vertex D is 7, but we already found a better path, 2. So this one is not updated as well. Unlike the previous situation, this time we found the path to vertex B, so we can consider what it offers. It has 2 neighbors, S and C, but none path is tempting to take. Moving on. As you can see, we can reach to C with 1, but in order to reach B, we pay 6, so 7 in total. Really unworth it. And to reach S, we need to go all the way to B, which equals 6 plus 2, so 8, but the path to S is 0. T doesn't offer any better path to reach its neighbor D, so we move on. Same with D. Since we finished this iteration without posting any updates, we can stop the algorithm and return the table. The runtime of this algorithm is OV multiplied by E. Well, that's the story. I hope you learned something new from this video, and please comment below with your thoughts. First degree studies in university are all about social studies, and this project comes to encourage that, even through complicated situations most of us are going through right now. Please subscribe to my channel and comment with your thoughts. I hope to see you soon. Good luck.